Okay, so welcome back to another video. So here we have something of a tricky trigonometric integral. So we have the definite integral from 0 to pi over 4 of the square root of tangent x divided by 1 plus sine of x times cosine of x and then dx. So again, this does look a little tricky at first glance, but we actually perform the right substitution. So a lot of this stuff is actually, of course, going to be relying on a whole lot of substitution. There's actually going to be a bunch of variables we'll be converting to. And then there's a step that I personally like that it actually looks difficult on how we actually want to rewrite this in a sense to where it will actually make the definite integral from that conversion a little bit easier than what it was originally proposed. So I won't say too much, but I will just give that a heads up. So nothing much to that. I think this one's an interesting one in the terms of, trigonometry and calculus put together into one. So why don't we actually just jump right in? First, this whole thing, we'll call this capital I, and then what I'll do is I'll actually multiply a secant squared x to both the numerator and denominator. So 0 pi over 4 of square root of tangent x, so multiplied by secant square of x, and then all this being divided by, so that means secant square of x multiplied this entire thing. It's just secant square x over here, and then I have sine x, cosine of x, which of course secant square of x is the same thing as 1 divided by cosine square of x, which actually just cancel out one of the cosines, and then we have a sine divided by cosine, which is simply just tangent x, and then dx. So with this in mind, so we can actually now simplify things even further to say that we can replace the identity for secant square of x to be tangent square of x plus 1. So put in that new substitution, so tangent x and then secant square of x divided by tangent square of x plus tangent of x and then plus 1 followed by dx. Okay, so now with this in mind, now let's actually perform a nice little u-substitution. So I'm pretty sure you can figure out what's the variable that, or rather the function we're going to be utilizing. So let's suppose that we let u equals tangent x, and then du is going to be equal to secant square of x, which is great. That is actually just cancel out that new differential with that substitution, and then we just replace everything in terms of u over here. So what we have now is, don't forget to change your bounds as well. So if I plug in pi over 4 for x, so that means u is going to be 1, and I plug in 0, then that's just going to be 0. So we have 0 to 1 of now just the square root of u divided by u squared plus u and then plus 1 followed by du. Let's now yet again do another u substitution. This time we're actually gonna now get a little creative here since we have a square root of u, so let's actually get rid of that radical. So we'll suppose we'll let u equals t squared, then that would have to mean that of course du is just going to equal to 2t dt, and then we actually just plug this right back in. So I'm just gonna go back to the black marker again. So what we have now is just plugging this back in. So nothing, the bounds doesn't really change when you put in the new bounds because it's going to stay the same when you plug it in, so that's great. So now we still have 0 to 1, and then now we have 2 times t with the new differential over here, so thankfully. So what we have now is I'll actually just put that together as 2t squared, and then divided by t to the power 4 plus t squared, and then plus 1, then dt. What we can do here now, before we get to the creative, spoiler alert, to the next favorite step, my favorite step, let's actually break this up of our numerator. So what I'll write is, so 0 to 1, and I can actually break this up in terms of t squared plus 1, and I'll put that as a quantity of its own, and then add this with t squared subtract 1, and then divide it by, so t to the power 4 plus t squared, and then plus 1 followed by dt. Okay, so now here comes the fun part. So we're gonna have to actually get our hands dirty here. So what we'll notice is that for the following denominator, t to the power 4 plus t squared plus 1, so I'll just write this full out again. We can actually decompose this a little bit differently, not in terms of factoring, but we can actually break the common like terms. In other words, this can be written as the same thing as t to the power 4 minus 2t squared plus 1, and then add this with 3t squared. And then another way you can write this, and this is very important on why I'm actually writing a second identity to what our original denominator is written as, is that this is written as t to the power 4 plus 2t squared plus 1, and then subtract t squared. With this identity, what we can do is we're actually going to break this up using the linearity of the integral over here. So first I'll write capital I, and then now we're breaking this up into 2 separate integrals into its own addition. So what we have now is going to be t squared plus 1 and then divided by. So we'll utilize this substitution for the first of the t squared plus 1 in its denominator. So t squared minus 2t squared plus 1 and then plus 3t squared, then followed by dt, and then follow with, so now add this with the same thing, so 0, 1 of t squared minus 1, all being divided by, so you utilize that substitution, t to the power 4 plus 2t squared plus 1, and then subtract t squared followed by dt. And so what we can do here is now we can actually suppose that I can now break this up. Well, not necessarily break it up yet. What we can do is now let's actually divide a t squared. So what that'll have is, and we're going to do the same thing to the other integral as well. So utilizing that, so 0 to 1 of now 1, and then add this with, I'm going to write this in the exponential form rather than it's a rational function. So t to the negative 2 power, and then all this being divided by, so if I actually multiply t to the negative 2 to everything down here, and then you can actually decompose this in a form of its factor of binomials. In other words, I can actually write this as the same thing as 1 plus, so the quantity on its own is going to be t, subtract t to the negative 1 quantity square, and then add this with 2 dt. Then we just apply the same thing over here, 0 to 1, so this is going to be 1, and then subtract t to the power negative 2, all being divided by, so now this is going to be 1 plus, and then t to the negative, or t, and then plus t to the negative 1 quantity square, and then subtract this with 2, and then dt. And then what's great about this is, guess what? Now we can actually perform more substitution, and then I think you can see where I'm going with this. So I'm actually going to do for back to u and then v. U is going to associate with our first integral, and then v is going to associate with our second integral. So we'll let u, we're going to let that equals t minus t to the negative 1. So of course differentiate, so du is just going to equal to 1, and then plus t to the negative 2 followed by dt. Then we start off with v, so v is going to be t, and then add this with t to the negative 1. Then dv is going to just equal to just 1, and then subtract t to the negative 2, and then followed by dt. Okay, so now with all of this, now we can actually now put everything together as a new integral as follows. And don't forget your change of bounds as well. So that means 0, 1 for over here. This is actually going to be from negative infinity to 0 of du, and then divided by u squared plus 3. And yeah, you can just add these terms together because it's just constants. So that's another step ahead. And now add this with, so now change the new bounds from over here. So I'm going to have a 2, and then this is going to be a positive infinity over here of dv, and then divided by v squared, and then minus 1. Okay. So now let's actually fix this up a little bit such that I have infinity and 2, so those needs to be switched. And what that means is that we actually have to change that addition sign to a minus. So now this actually now fixes everything up. Okay, so now this is the most common antiderivative over here, so we can actually find that. That's actually going to be written as 1 divided by the square root of 3 multiplied with arctan of u divided by the square root of 3, and then evaluate your bounds from negative infinity to 0. And then next we have is just, we're going to leave that as a standalone integral from, what is it, 2, positive 2 to infinity of dv divided by v squared minus 1. Okay, so plug in 0, you're going to get a 0. Plug in negative infinity, you're going to get negative pi divided by 2 times the square root of 3. So we do the subtraction, so that would actually give us with a positive. So now that'll just actually give us with pi divided by 2 times the square root of 3. And then over here, all you have to do is just, of course, apply the partial fraction decomposition, which is a fairly simple exercise. I'll just skip that step. Another thing we're actually going to take is we're actually going to do adding a 0 term to that sense. And what that'll give us is that I have now a minus, then 1/2, then multiply with the integral from 2 to infinity of, now this is going to yield us with v plus 1, and then subtract v minus 1 divided by v plus 1 multiplied by v minus 1, and then dv. Okay, and so from here, that of course this is actually straightforward, that you could actually break up again by using even more linearity to say that I have, so pi to square root of 3, and then we break this up, so minus 1/2, and then the integral from, what is it, 2 to infinity of 1 divided by v minus 1 dv, and then the next one I have is minus the integral from 2 to infinity of 1 divided by v plus 1 dv. Okay, and then simply straightforward that we can actually just apply we know the antiderivatives, and then we plug in our bounds. And then also the same thing is that we notice that they're both its antiderivative is gonna be the natural log. So why don't we actually combine both together into a single logarithm? So now I have pi divided by 2 times the square root of 3, then minus 1/2, then the ln. So let me actually put this in terms of the absolute value. So minus b minus 1 and then b plus 1. So that kind of leads to an issue that we have, that this is actually, we have infinity and then 2. Actually put the parentheses over here. So 2 and then infinity. So what I can do is, of course, let's actually just divide a v, so at least we have something of a rational function that we're actually working around with. So pi divided by 2 square root of 3 minus 1/2, and then the natural log of, so I have 1 minus 1 divided by v, and then 1 plus 1 divided by v right here. So that means from infinity to 2 over here. And so what we have is that if you plug all of this back together, I have an ln of 1/2 divided by 3 over 2. If you simplify that together, I have now just pi divided by 2 square root of 3, and then add this with 1/2 times ln of 1 over 3. Let me actually move it to that little space over here that we can actually simplify even further to get our nice final answer. And also notice that I can actually factor out a 1/2 as well to say that we have that the final answer, so capital I, is going to equal to 1/2 and then multiply by pi divided by the square root of 3 and then subtract ln of 3, which of course that is actually our final answer. That actually is a very neat value. And with all this crazy substitutions that we've been doing, u-substitutions, then a lot of u-substitutions essentially, and then breaking it up such that we have something in this form, because we have something tricky with the 4th power of that polynomial, that it actually yields to something so beautiful that we actually come to some, a basic result, if you want to call it basic. So yeah, that's pretty cool if you ask me.